In this next unit, you're going to start taking a look at conic sections. And so what we want to do is we want to go back to what you learned in geometry when we were working with three-dimensional objects. We talked about in geometry, if you've got a three-dimensional object and you put a plane through it, either vertically or horizontally, you're going to get a certain shape out of that. So if we were to take this prism, this is a six-sided or hexagonal prism, and if we were to just cut this in half or put a horizontal plane through it, then what we would say is you would rotate it, and that's going to give you the shape of what that cross section is going to look like. So if you put a horizontal plane through a hexagonal prism, you're going to get the shape of a hexagon. You'd then be able to take that area and do all sorts of things with it. You could write equations based off of it. If you were to take a cross section of a sphere, you can cut the sphere this way, here, you can cut the sphere any way. It doesn't matter which way you cut the sphere, you're always going to end up with a circle. If we were to take a cylinder and we were to do cross sections with a cylinder, then what you would see is if we do a horizontal plane, you would end up with a circle. But if we did a vertical plane, and let's say that, if you could imagine taking this front part off of this cylinder and taking it away, what shape would you be left with? What would you be able to see? You would end up getting a rectangle there. Now what we're going to do with conic sections is we're going to use cones. So with the cone, we're actually going to use a double-sided or a double cone here, just like this. So imagine you have this one with another one right underneath it. And what we're going to do is we're going to try all of these different planes cutting through and intersecting these cones at different angles, and we're going to look at the shapes or what's left over when we do those cuttings. So the first one that we're going to take a look at is we're going to take a look at a horizontal plane through one of these cones. So imagine if you cut a horizontal plane through this cone. What would you end up with? So this is the two-dimensional version of this three-dimensional object. This is how we have to show it on the board. So remember that your rectangle is going to indicate your plane, and then we've got the sphere, and the backside of the sphere is indicated by that dashed line. You can see that where the plane intersects the cone, you create this shape right here. Now, because we're looking at it from side view, we don't actually see what the shape looks like. So what we want to do is we want to take that cone and we want to rotate it so that you either have a top view or rotate it so that you have a bottom view. So when we do that, you can see that here is our plane here outlined in the pink, the same as what you saw here. And then here is the top of the cone indicated by the point, and here's the bottom of the cone indicated by the broader circle. So what we see is that when we end up putting this horizontal plane through this cone, we end up getting a circle out of that. Now what we can do is we can take the information that we've got and we can figure out what is the area of that circle. We can figure out the circumference of it. We can do a whole lot with just a little bit of information. The formulas that we're going to use whenever we're looking at circles, we're either going to use the general or vertex formula, or we're going to use the standard formula. So if we use the general or vertex form, it's going to look a lot like what we did with parabolas, radicals, with rational family. There's a whole lot of things that you've already applied this particular formula to. You'll notice that you've got h and k, and then over here we've got an r squared. So with the h, that again is going to indicate our horizontal movement. So we're going to be moving left or right away from the center or from the origin. And then our k value is moving up or down, and that's again up or down away from the origin. The r squared, the r indicates the radius. So if this number is say 25, that tells you that your radius is 5, because in order to get rid of that square, you've got to take the square root. And so you would know exactly what your radius is, and you would know where the location of the circle is on the graph. If you have x squared plus y squared equals r squared, if we don't have any movement left or right, this is all we're going to have here, x squared plus y squared. And then the r squared again is going to indicate what our radius is going to be by taking the square root of whatever number that is. Now we're going to take a look at problem number 1 and see how this is applied. In problem number 1, we're going to be asked to graph x squared plus y squared equals 25. There's really only 3 pieces of information that you need to know in order to be able to graph a circle. The first one is going to be your h value, the second one is your k value, and the third one is going to be your radius. So if we look at the equation that we've been given, the x squared plus y squared equals 25, you notice that this is in standard form rather than the general or vertex form that we've become accustomed to. So that tells us automatically our h value and our k value are both going to be 0. So that means the center of our circle is going to be at the point 0, 0. So I may even ask you later, what is the center of the circle? And then you would just indicate that the point is going to be 0, 0. From here on out, we've only got to find 4 points, and this is actually pretty easy. We take 25 and we take the square root of it. So the square root of 25 is going to be 5. That tells us that our radius is going to be 5. So all we're going to do now is we're going to use the 4 cardinal directions, north, south, east, and west, and we're going to go 5 units in each of those directions in order to give us a point, 4 points on the circle itself. So we go 1, 2, 3, 4, 5, and there's your first point. 1, 2, 3, 4, 5. There's your second point. 1, 2, 3, 4, 5. And then again, 1, 2, 3, 4, 5. So now we have 4 points that we know are on the edge of the circle. All we have to do now is to connect them. This is really the hardest part about drawing circles, is drawing the circle itself. So we're going to go, just do this the best you can. Again, this is not very easy. But there you go. It's not even close to being a perfect circle, but that's exactly what you're looking to do. Because we've got 4 points on the circle, we know that those 4 points are on the circle, and just because we weren't able to draw a perfect one doesn't mean that it's not a correct answer. So the next type of plane that we're going to look at through the conic, through the double cone, is going to be a diagonal plane that goes through the lateral sides of that cone. And you can see that what happens is when you get this diagonal plane going through there, we no longer get a circle. We instead get this elongated shape. It's like taking a circle and pulling it by its ends. And so you get, it's thinner here, but it gets longer as it goes along. And so if we were to take, again, this two-dimensional shape and rotate it 180 degrees towards you, or I'm sorry, 90 degrees towards you, what we're going to see is that, again, this is the top right here. This is the point of the cone. This is the bottom of the cone. And this is the resulting shape from when we put the diagonal plane through the cone. We get what is known as an ellipse. Now, the ellipse, again, you're going to recognize these formulas. They look a whole lot like standard form of a lot of equations, and they also look like the general vertex form of a lot of equations. They also look very, very much alike the circle formulas. So if we take, remember that the circle formula for standard form was x squared plus y squared equals r squared. So for an ellipse, it's going to be x squared over a squared plus y squared over b squared equals 1. And what happens is when we get this a and this b introduced, that's what's going to give us some of that stretch that we get with the ellipse. Because remember that when we're talking about the a value in the vertex form of any sort of equation, we're talking about stretching, compressing, and reflecting. So a and b are going to be your stretch and compress. The vertex form is going to be x minus a squared over a squared plus y minus k squared over b squared equals 1. So again, we see that these both of these equations look very, very similar to the ones that we've already seen for circles. So for problem number 2, we're going to graph an ellipse. And what I'm going to do is I'm going to show you a couple of different methods that are not in the book for being able to solve this problem. So what we know when we look at the equation for an ellipse is that we want to get to the point where we've got an equation that looks like this: x squared over a squared plus y squared over b squared equals 1. So in order to be able to get down to this equation right here, where we have the x squared over the a squared, the y squared over the b squared, and then especially right here, where what they're equal to is 1, that means that we need to divide this side by 144. Okay, so we're going to start by doing that. And what you may notice when we do this is that there's a pattern that comes out with these two numbers here. So we're going to divide everything by 144. So when we do that, 16 times 9 just happens to be 144. So these two numbers end up switching places. So we're going to end up here with x squared over 16 and y squared over 9 equals 1. Now the next thing that we're going to do to figure out how we're going to graph this is to this. We're going to take the square root of 16. So a squared is equal to 16. So that tells us that a is equal to both plus and minus 4. Okay? Now we're going to write this down because this is going to be our horizontal stretch right here. So a is going to represent the horizontal stretch, and that's going to tell us to go plus or minus 4 units away from the center of our ellipse. Now for the y squared or the b squared here, we're going to go b squared equals 9, and so b is equal to plus or minus 3. So we go over here, and we're going to write down b is equal to plus or minus 3. This is going to be our vertical stretch away from the center of the circle, or I'm sorry, from the center of the ellipse. Now on this particular problem, what we could have done is this. We could have just gone back here to the beginning and said, if I take the square root of 9, that's going to give me b. If I take the square root of 16, it's going to give me a. So it was actually the opposites of what we would normally think. And so that's another way of looking at it. Instead of going through and doing all the mathematics to get to there, you could have taken the square root of 9 and the square root of 16, and that would have given you both a and b. Now that may or may not work in every situation, so be careful how you use that. You may just want to go ahead and stick to the 144 and dividing that all the way through every term in the equation. So the way that this works is when we go to graph this, since we have no h or k values, that means that the center is going to again be at 0, 0. The a represents our x-intercepts. So we're going to go 1 unit, 2, 3, and 4, and then 1 unit, 2, 3, and 4. And so there is our stretch horizontally away from that center. Now, when we look at the b value, that's going to give us our y-intercepts. So our y-intercepts are going to be a plus or minus 3. So go 1, 2, and 3, and then 1, 2, and 3. And now you have enough information to be able to graph this. So we're going to just go ahead and connect this together, and we're going to get a shape that looks like that. Now the next type of conic section that we're going to take a look at is called a hyperbola. And hyperbolas are going to be created by taking a vertical plane and running it through both cones. So you can see that when we do this, we end up getting these two symmetrical, they almost look like mouse holes, like if you've ever seen the old cartoon where the hole in the wall where the mouse goes in. So yeah, they're going to be symmetrical based on this middle point here. So if we take this and we rotate this down 90 degrees, you can see that we've got our double cones right here. And then we're going to get this symmetry of these two hyperbolas right there. The equations for hyperbolas, they're going to look a lot like both circles and ellipses, except we're going to take that positive, we're going to change that to a negative. So we're going to have x squared over a squared minus y squared over b squared equals 1. And then the vertex or general form, x minus a squared over a squared minus y minus k squared over b squared equals 1. And we'll go ahead and take a look at another problem to see exactly how this works. For problem number 3, we're given an equation and we're asked to graph the hyperbola that results from it. So what we're going to do is we're going to start with x squared minus y squared equals 9. And again, we're going to take that, whatever's on the right side, and we're going to make that become equal to 1. So to do that, I'm going to go ahead and rewrite the original equation, x squared minus y squared equals 9. And I'm going to divide everything by 9. So it's going to result in x squared over 9 minus y squared over 9 is equal to 1. What I then want to do is I want to take the square roots of both the a squared and the b squared to determine where are the stretches going to be. And so we're going to get a is equal to 3 and b is equal to 3. What this is going to tell me is that this is going to start here and here. So our y-intercept, or I'm sorry, our x-intercept is going to be at 3 and negative 3. The next thing that we're going to do is we're going to choose a point to the right of this x-intercept, which the easiest one for us to do is going to be 4. So we're going to take 4 and we're going to plug it into the original equation for x, and we're going to see what the y value is. Now remember that because these two are symmetrical, whatever I do over here to 4, I'm going to have the same result for negative 4. So I don't have to do both of them. I only have to do one and then just draw in the exact same thing on either side of the graph. So if I plug in 4 for x, I get 4 squared minus y squared is equal to 9. So 16 minus y squared is equal to 9. Negative y squared is equal to negative 7. Y squared is equal to 7. And so y is equal to plus or minus the square root of 7. Now because the radicand 7 is between 4 and 9, we know that the solution is somewhere between 2 and 3. I'm not going to go and calculate this out because I can just guesstimate this on the graph. So I'm going to go over to 4 and go up 1, 2, and then right about there. Now remember that this is plus or minus, so I'm going to go above and below on this graph. So 2, 3, it's going to be right about there. And then I'm just going to go ahead and draw this in. Okay. So there's the right side of it. Do the exact same thing on the left side. Use these exact same points right here for y. Just go over here and plug them in on x equals negative 4. And then sketch in a smooth graph. And there you have your hyperbolas. The last type of plane that we've got that we're going to look at is going to be the diagonal plane that goes through the lateral face and the base of the cone. Now what's going to happen when we have this particular diagonal plane is that we're going to end up with a parabola that is going to be created through the intersection. Now remember, you've done lots of work with parabolas already. We've done these in Algebra 1 and Algebra 2 already. And a parabola has the formula, or has the equation y equals x squared, or the vertex form y equals x minus h squared plus k. We don't have any examples for this particular section, but we will be looking at them in the next section.